This is our last video for chapter 20, and we will be looking at reactions of nitriles. The first important reaction that I wanted to talk about is the hydrolysis of nitriles. So we've already seen this with respect to preparation of carboxylic acids. So if we're starting with an alkyl halide, treat it with cyanide to give the nitrile. And then this can be hydrolyzed to give the carboxylic acid. There is an H there. Alternatively, if we make a cyanohydrin, keep in mind dilute acid will be sufficient to protonate the O-, and then more concentrated acid is required to convert the nitrile to a carboxylic acid. And in this case, we get a alpha hydroxy carboxylic acid. In case you're interested in how this reaction works, if we have a nitrile and we react it with H3O+, this would have to be pretty concentrated. The nitrogen can grab a proton, and that will give us a protonated nitrile, where this nitrogen has a positive formal charge. That is going to make the nitrile carbon more electrophilic, so water can now add to this carbon, pushing these electrons onto the nitrogen. So this is a double bond, lone pair, hydrogen. The carbon is connected to oxygen, which is still connected to the two hydrogens. It has one lone pair and a positive formal charge. There will be another proton transfer. Water can grab off this proton, giving an imine. Actually, that's not an imine because it also has the OH. I'm sure there's a name for that. This can get protonated again. And keep in mind, if the oxygen grabs a proton, we're just going backwards, and so that's going to happen. This is an equilibrium. But if the nitrogen grabs a proton, then we get something else. So let's picture that, and that is going to give us NHH plus H. Now, oxygen can share electrons with the carbon, putting electrons onto the nitrogen. And another proton transfer will give an amide. Hydrolysis of a nitrile leads to an amide, but that's not yet the end of the reaction. So we're still looking at the hydrolysis of a nitrile, and on the last slide we saw that it goes to form an amide. So from here, we're still under acidic conditions, so the oxygen can grab a proton, and water can act as a nucleophile, pushing these electrons up onto the oxygen. Giving this intermediate. Next, we would have a couple of proton transfers. So water can grab off one of these protons, and H3O plus can give up a proton to the nitrogen, and that would give this intermediate. These electrons can restore the carbonyl, kicking out, in this case, NH3. And then finally, one more proton transfer gives the carboxylic acid. Now, this was just in case you're interested. In the next chapter, we're going to talk a lot about these reactions. So the hydrolysis of amide is related to a number of reactions of acid chlorides and of esters. And so we are going to look through these. I just wanted to go over this in case you wanted to know how this works. I'm not going to ask you to repeat the mechanism for the hydrolysis of a nitrile. In this case, I want you to be able to predict the products, to recognize the reaction conditions, and predict the products. But I'm not going to ask you for the detailed mechanism. Nitriles can be reduced with lithium aluminum hydride to give an amine. So 2 hydrogens are added to the carbon of the nitrile, and 2 hydrogens are added to the nitrogen of the nitrile. These 2 hydrogens both come from the lithium aluminum hydride reagent, and these 2 hydrogens both come from water. You are not responsible for the mechanism, but I'm just going to go over this in case you are curious. So keep in mind, lithium aluminum hydride is a source of hydride ion. And so this can donate its electrons to the nitrile carbon, pushing these electrons onto the nitrogen. So now we have 2 lone pairs on the nitrogen, and it has a negative formal charge. And this is, the carbon is now connected to a hydrogen, which came from the lithium aluminum hydride. Now, another equivalent of hydride can add, and this is one that probably doesn't seem very believable, and it's because I am skipping some details, but that would give us a single bond to nitrogen with 3 lone pairs and a charge of -2, and a hydrogen connected to the carbon. So the detail that I'm skipping is that because we started out with lithium aluminum hydride, when we donate a hydride, we now have aluminum trihydride, which is going to have a positive charge. So in these intermediates, this nitrogen is going to be complexed with some aluminum species, which makes this more reasonable. Okay, and then when this is worked up with water, this can grab a proton and this can grab another proton, and that will bring us to H and H. So the nitrogen still has 1 lone pair. Again, notice this was our hydride and this was our hydride. So this is our hydride. So in the end, these 2 hydrogens came as hydrides. And then this and this came as protons from the water. So if you want to know how this works, then here is some information. Mainly what I want you to know is that nitriles can be reduced by lithium aluminum hydride to give an amine. The last reaction of nitriles that we're going to talk about is the reaction with Grignard reagents. Now, one thing I forgot to mention, when we think about a carbonyl compared to a nitrile, with aldehydes and ketones, we just talked about a whole bunch of nucleophilic additions, and so we had already talked about Grignards and organolithium reagents. But then we also talked about adding an amine or an alcohol or cyanide. So all of these milder nucleophiles can add to an aldehyde or a ketone. But those milder nucleophiles cannot add to a nitrile. So this carbon is not nearly as electrophilic as this carbon. The one exception, though, is if we have a really good nucleophile, such as H-, which we just saw on the previous slide, or R-, which is what we have with a Grignard. Grignard reagents can add to nitriles. The product, though, might look a little surprising because what you end up with is a ketone. So notice this piece becomes this piece, and this ends up here. All right, so what's happening? Just as you would expect, the Grignard is a source of a nucleophilic carbon, so this is going to share electrons with the carbon, pushing these electrons onto the nitrogen. Let's see if I can stick with color coding. So this is the CH3 from the Grignard reagent. Next, on aqueous acid workup, the nitrogen, first of all, can grab a proton, and we will get this intermediate. Notice this is an imine. And keep in mind, we saw a couple of chapters ago that if you had an aldehyde and you reacted it with an amine, that would give you an imine. Well, keep in mind, these reactions are reversible, so the aldehyde plus the amine gives you an imine plus water. Well, here we have lots of water and we have an imine, so this reaction is reversible. Sorry, I'm going to fix this here. Okay, so we've got more H3O+, so the nitrogen can grab another proton, and that will give CH3, C double bond N. So these hydrogens are coming from water, and this came from the Grignard. And now nitrogen has a positive formal charge. Water can add here, okay, pushing these electrons here. This gives H3C single bond N, H2 and a lone pair. And this is the CH3 that came from the Grignard, and this is from water. This can go through a couple of proton transfer steps. Remember, we have water, we have H3O+, so the nitrogen can grab a proton from here, water can grab a proton from here, and I need to write this really small. This will give us the CH3C NH3 plus connected to OH connected to CH3 that came from the Grignard. Next, one of these lone pairs can form a carbonyl, kicking out ammonia, and that is going to give us CH3C double bond OH plus and the CH3. And then finally, one more proton transfer step. This can grab off a proton, put these electrons back here, and we get a ketone. So the Grignard adds to the nitrile carbon, and after some proton transfers, it leads to an imine, and then the imine undergoes the reverse of nucleophilic addition of ammonia to an aldehyde or ketone, right? It goes through the reverse so that the isolated product is the ketone. In this case, ammonia, this would be kicked out here. That would just be bubbled off as a byproduct. So in general, I think it's helpful to be able to follow the electrons here, think about an acid-base step here, and then just recognize that this is the reverse of nucleophilic addition to an aldehyde or ketone to be able to predict the final product. So remember, what was the nitrile is now a carbonyl containing compound, and what was the Grignard is now connected to the new carbonyl carbon. So this takes us to the end of chapter 20. We went over some general information, including naming, bonding, spectroscopy. We talked more about carboxylic acids and phenols in terms of their acidity, including structure and acid strength. Then we focused on preparation of carboxylic acids, and we just mentioned some reactions of carboxylic acids. We're going to look at more of these next chapter. And then finally, we looked at nitriles. We talked about preparation, and we talked about some of their reactions as well. By now, we have so many different types of carbon-carbon bond-forming reactions, as well as functional group interconversions, that while it can be overwhelming, I want you to recognize that you now have lots of tools in your synthetic toolbox.